All right. Good morning, good afternoon, good evening, everyone. Welcome to today's webinar organized by the International Society for Biopharmaceutical Statistics. My name is Dong Xi. I'm from Gilead. I'm your host today. Today, we're going to have a very exciting topic on covariate adjustment. And we're grateful to have our speaker today, Ting Ye, who is assistant professor in biostatistics at the University of Washington. Her research aims to accelerate human health advances through data-driven discovery, development, and delivery of clinical, medical, and scientific breakthroughs, spanning the design and analysis of complex, innovative clinical trials, causal inference in biomedical big data, and quantitative medical research. Ting is a recipient of the School of Public Health Genentech Endowed Professorship and the NIH Maximizing Investigators Research Award. Ting is a true leader in covariate adjustment for randomized clinical trials. She has published over 10 papers, including 4 in top-tier journals such as JASA, JRSSB, and Biometrica, 2 of which have been cited in the FDA's official guidance on covariate adjustment. The Robin Carr R package, developed by her research group, has become a standard software tool in the field. She's also a co-founder and co-chair of the ASA Biopharmaceutical Section Scientific Working Group on covariate adjustment. So without further ado, I'll hand over to Ting. Thank you very much.
Thank you so much, Don, for the kind invitation and the very kind introduction. Thanks everyone for joining. It's great to see a lot of people online. Today, I'll talk about covariate adjustment in randomized clinical trials and from general theory to practical insights. This is a series of work that I did with my amazing collaborators, my student Marlena, and my long-term collaborators, Dr. Jun Shao, Qingyuan Zhao, Yu Du, Jingyi Liu, and Yan Yaoyi. So I'll start with what do we mean by covariate adjustment and why do we adjust for covariates? Covariate adjustment can happen at 2 stages. One is at design stage, where we usually do covariate-adaptive randomization or stratified randomization as like special examples of covariate-adaptive randomization. And this can be done to balance across baseline covariates to gain credibility and efficiency. Most commonly used covariate-adaptive randomization include the stratified permuted block randomization and also Pocock and Simon minimization if you want to balance more covariates. And covariate adjustment also happen in the design stage. In the analysis stage. And in the analysis stage, we consider model-assisted analysis, which leads to more efficient use of data under minimal assumptions required by the unadjusted analysis. And in the talk, I'll mostly focus on how we do analysis in the analysis stage, but we will keep in mind that we usually also have done covariate adjustment in the design stage by covariate-adaptive randomization. And before diving in, I'll just talk about what my covariate adjustment workflow is. In traditional regression class, we learn about linear model and the interpretation of the coefficients are dependent on what covariates we put into the model and the model correctness. But this is different from the covariate adjustment workflow that I'll talk about today. So the workflow, as we are familiar with this graph in the ICH E9R1 addendum, currently the covariate adjustment workflow starts by define estimand. So we first define estimand of interest based on clinical relevance. And then we consider what estimation methods we will use. It can be unadjusted methods or it can be covariate adjusted methods. So the covariate adjustment are used to improve efficiency of this defined estimand and under approximately the same assumption in the unadjusted analysis. So the goal is to do not change the estimand of interest and also improve efficiency without further assumption required. Okay, so I'll first start with covariate adjustment in the non-survival setting with either continuous or discrete outcomes. And then I'll move on to covariate adjustment for survival analysis. So my focus will be on the unconditional estimate, which is any comparison of these unconditional expected values of outcome means across different arms. And for full general framework, we consider multiple arms. We have K treatment arms. And so the easiest method to estimate this estimate is the unadjusted method, which is just a simple average outcome mean across different arms. Or we can also use like a saturated model, which include different treatment indicators, and the coefficients will estimate will exactly be the average outcome means across arms, and that's what we know as an ANOVA, analysis of variance. So this is the unadjusted method that we will use as benchmark. And yeah, so the unadjusted analysis is just simple sample mean of observed responses within different treatment groups. Then we can also do linear adjustment, which is common for continuous outcome. And for linear adjustment, we usually fit a linear model, and this is what we call a working model, because we will use this model to derive an estimate, and the correctness of that estimate will not rely on the correctness of this model. So we fit a linear model, which can have treatment by covariate interaction, allowing the beta, the coefficient in front of x, to differ by treatment, or it can put restriction on the beta to be all equal. Then this is the analysis of covariance that include only the treatment and the covariates. But in any case, we can use this model to get the effect of interest. Sorry, to get the estimator of interest. That's the written here. So if we do ANCOVA, which is just all the beta equal to each other, then the average treatment effect comparing arm 2 and arm 1 are just obtained from the coefficient. So you don't need this formula. This can coincide with the coefficient in front of the treatment indicator. But this formula will give us more general because it's estimating all the unconditional outcome means. And as we can see, the unadjusted estimator is a special case of linear adjustment with all the beta equal to 0. So we can see the linear adjustment is a more general form. And if we restrict all the beta to be equal in this working model, then the resulting estimator is just the ANCOVA estimator. And in a paper by Tiatis in 2008, and also later by our paper in 2023, we studied the estimator that include treatment by covariate interaction, and which is called ANCOVA2 in the literature, and also we name it as analysis of heterogeneous covariance estimator, ANCOVA, in our 2023 paper. So this estimator do not restrict all the beta to be equal, which allow for treatment by covariate interaction. And this model has not traditionally been commonly used in the literature because when we have treatment by covariate interaction, it's hard to interpret the coefficient as treatment effect estimate. But now with the estimate framework and this model assisted approach, it's not a problem because we can just fit this model and then calculate in this way, and this will always be estimating the estimate that we define. So this ANCOVA estimator also has nice theoretical property. It has guaranteed efficiency gain over unadjusted estimator. So this means that even when the true outcome model is very far from a linear model, the ANCOVA estimator will always be more efficient asymptotically than the unadjusted estimator. So that's nice. We have some guarantee that covariate adjustment will do no harm. And this is different for the ANCOVA estimator, which do not include treatment by covariate interaction. So it's possible that when the treatment covariate interaction indeed exists, then the ANCOVA can lose efficiency over the unadjusted estimator. The next I'll talk about is the G-computation. The G-computation basically extends linear adjustment to generalized linear models, which fit a generalized linear model, and we can include the covariate in ways that we like, with or without treatment by covariate interaction. And then once we fit this model, we will use this model to obtain the predicted probability in my binary case, or the predicted mean value for everyone in the trial for every treatment arms. So this is, for example, if we have n participants, this type of average will create n by k matrix of all the predicted values for everyone under different treatment arms. And once we have that, we can show that this is a estimator of the estimate that we define, which is just an unconditional outcome mean. And a representative estimator is the G-computation using logistic regression that's described in detail in the FDA guidance. But one thing that what I want to note that is we can see the linear adjusted estimator is a special case of G-computation with identity link. So this is also a more general formula than the above two. But the G-computation has caveats. The link function needs to satisfy a property called prediction unbiasedness for the G-computation estimator to be asymptotically unbiased. As you can see, because this estimator can take just arbitrary misspecified models, there's no guarantee that this will always correctly, consistently estimate the estimate. But what's nice about this is that if we work with canonical link function for GLM, then there's guarantee that this will always be consistent. So that's satisfying prediction unbiasedness. So here I just give example of that G-computation can really potentially be biased if not careful using non-canonical link functions. So in this case, I just do a simple simulation with potential outcomes being counted. They are generated from the negative binomial distribution with the same dispersion parameters. And then we do simple randomization with unequal randomization ratio, and the parameter of interest is the average treatment effect. And here we consider two estimation methods. One is using Poisson regression, which is a misspecified model, but this is a canonical link for GLM. And the second is negative binomial regression with unknown dispersion parameter. So we can see that if we run simulation, and these are the simulation bias and standard deviation, we can see the G-computation using Poisson regression, although it's a misspecified model, it has very little bias compared to the standard deviation. But the G-computation with negative binomial with unknown dispersion parameter has quite large bias, which is about 1/2 of the standard deviation. So this is to re-emphasize the point that the Poisson regression using log link, which is a canonical link, and therefore the G-computation by some nice theoretical property is unbiased. But negative binomial regression with unknown dispersion parameter that's estimated by maximum likelihood is not a GLM with canonical link, and therefore the G-computation is biased. So that's not nice because we don't want to restrict to only canonical link GLM. So what can we do? It's actually quite simple. We can easily correct the bias, and this leads us to the AIPW estimator. This is called augmented inverse propensity weighting estimator, or sometimes known as doubly robust estimator. So this estimator will fit arbitrary model, which we denote as mu A. And it doesn't matter if this model is fitted using like canonical link GLM, it can be quite arbitrary. And once we have that model, we will take that model to construct the estimator. And when we do construction, this is the AIP form, which has two parts, as you can see. This part is exactly the same as the G-computation. It's just the average across all the participants under the model fitted for treatment arm A. And then we know that this may have bias. Then we have this additional term, which is the residual, or just basically this is estimating the bias of using this model in the treatment arm A data. And then subtract the bias. So this bias term that we estimated from the arm A data, because it's representative of the whole population, so it's also the bias for the whole population, and therefore this term minus this term, or this term plus this form, will give us the correct, will always give us consistent estimator of the estimate. So we can see that the G-computation estimator is also a special case of AIPW when we have this model satisfy prediction on biasness, which means that this correction term will exactly be 0. But if we have G-computation have bias, then this term will not be 0, but the AIPW will be correct and G-computation is not. So slightly more technical way to understanding the AIPW is that if this model that we fit, the mu A, if it satisfies downskirt condition, which means the model class is not too complex, all the parametric models satisfy downskirt class. There's also other models satisfy downskirt class. And then because the AIPW is known to be doubly robust, in the sense that if the outcome model or the propensity score model is correctly specified, then this estimator is consistent. And in clinical trial, we are in a good shape because the propensity score, which is the probability of treatment assignment, we know the truth. That doesn't depend on any variables. It's just a constant treatment propensity. So this is always correctly specified. And therefore, we have guarantee that we can have outcome model be arbitrarily misspecified, but this AIPW estimator is always consistent. So this is just to return to the example we showed earlier. If we use AIPW estimator, regardless of using Poisson regression or negative binomial regression, the estimator will be always unbiased. And so in this case, you can see the AIPW with Poisson and G-computation with Poisson is almost the same. They are indeed almost the same because Poisson satisfies the prediction on biasness property. So you can see that the AIPW is more general and more robust than G-computation because when G-computation works, it's the same as G-computation. But when G-computation is biased, AIPW corrects the bias. So going back to the AIPW estimator here, the working model mu A can also be estimated using machine learning methods like random forest or using ensemble methods. And that's also one advantage of the AIPW approach because it allows for that. But if we do machine learning, then we need to do cross-fitting. And I won't talk into the detail, but the cross-fitting is needed for the estimator to be asymptotic unbiased if we use machine learning methods, and also for valid inference if using machine learning methods. So now we can see the AIPW estimator is the general form of covariate adjustment in randomized clinical trials. It's proved in Tiate's 2008 paper that all the consistent estimators of this estimand can be written in this form, or is asymptotically equivalent to this form. So this is indeed the general form of covariate adjustment in randomized clinical trials. And therefore, we studied this AIPW estimator so that we have a unified theory for all the covariate adjustment methods. So the next couple of slides, I'll talk about a few theoretical results. It's a bit technical, but I'll explain them, and it's okay, you just get the big picture. So the AIPW estimator defined here, we study its asymptotic distribution under covariate-adaptive randomization, which again includes simple randomization as a special case, but also include stratified permutive block and Pocock assignment minimization methods. So we collect this vector of estimators for the estimand, and then we show that this estimator is always centered at the estimand without any modeling assumption, and it's asymptotically normal. And we can derive the variance for this estimator. So this variance will be a matrix, a variance covariance matrix, and it has multiple parts. So as we can see, this part is related to the residual, the variance of the residual, and this part are about some covariance and variance for the model that we fit in the outcome. And also we have this additional term in blue. This is the variance reduction because we do covariate-adaptive randomization. So we can see how the covariate-adaptive randomization affects the asymptotic distribution of the estimator. And under simple randomization, we have a slightly simpler formula. That is, we don't have the last term. So this is just the formula for the simple randomization. And once we have this asymptotic distribution, then it's quite easy to derive asymptotic variance for any contrast of these estimators. Like if we're interested in average treatment effect, which will be the difference of two estimators, or like ratio of two estimators, which is more common in the count data setting, or even odds ratio of these estimators, then it's very easy to apply delta method to obtain the variance for the contrast. And we also propose plug-in variance estimators for estimating the variance, which is also fully robust and always consistent. So in practice, you wouldn't need to derive any of these delta methods because we have implemented all this in the R package. And I just have a couple of notes about the efficiency. So for the efficiency, I already mentioned that if we do ANYCOVA, which is the linear model that includes treatment by covariate interaction, and furthermore, if we do covariate-adaptive randomization, then if we include this stratification factor that we use in covariate-adaptive randomization in the adjustment of linear model, then this approach has guaranteed efficiency gain, and its inference is also universal under all commonly used covariate-adaptive randomizations. This is nice because we can use the same estimator, and its asymptotic variance is the same across different randomization schemes. So we don't need to tailor or adjust the variance because we do stratified randomization. And for the G-computation, the story is a bit different. You may wonder, do we have no harm guarantee if we do like G-computation with the logistic regression? So I want to say in theory, there's no harm guarantee because like it's possible to construct scenario where using logistic regression, the G-computation is less efficient than the unadjusted method. However, that wouldn't appear quite often in practice because we have to design a quite artificial scenario for that to happen. But that still illustrates the point that there's no harm guarantee for nonlinear adjustment. But we can still achieve nonlinear adjustments guaranteed efficiency again by some simple correction. So we know that the G-computation, just to illustrate the point I said, the G-computation, if we include the stratification factor in the model, and this estimator has universal inference under all the commonly used covariate-adaptive randomization, but it does not have guaranteed efficiency gain. There's a very nice paper by Cohen and Gotti in 2023 in Biometrica that proposed using linear calibration on the G-computation approach. So the main idea is that once we fit the G-computation, like fit these nonlinear models, we will take them as our super covariates and then refit a linear model. And because linear model, especially the ANYCOVA, give us no harm guarantee, so that restore guarantee efficiency gain. But this approach only works for simple randomization, so we extend it to covariate-adaptive randomization. So in other words, to achieve no harm guarantee under all covariate-adaptive randomization, and also achieve universal applicability simultaneously, we need to take the nonlinear model fitting as well as take the stratification factor and refit them using a linear model. The final predicted values will be our final used predictions. And then we take this plugin into the AIPW estimator, and that final estimator will have no harm guarantee and universal applicability simultaneously. So all the methods I discussed and beyond are available in our package, Robin Carr. And this package is now available in both Cray and GitHub. So now let's move on to survival analysis. Survival analysis has different flavor than non-survival setting. In non-survival setting, we have seen that we can fit outcome model and then construct an estimator using the fitted value of that outcome model. But in survival setting, because with censoring, we cannot easily just fit model for the time to event. So the usual model that we fit is Cox regression or other like AFT models. So they target different estimates. So there's always not so clear how to do covariate adjustment in survival analysis. But right now, with the more modern like workflow that I talked about, first we define estimate and then we think about how to do covariate adjustment for the estimate. This has been more clear now, so we can still separate the estimate and covariate adjustment. And here I list just a bunch of estimates that's commonly considered in current survival trials, which include survival function, unconditional survival function per arm. This is usually estimated by Kaplan-Meier. This is the unadjusted method. And it assumes the independent censoring assumption. And another estimate we care about is like unconditional hazard function per arm. And if we want to test the null hypothesis that the unconditional hazard function is equal for two arms, then we use log rank test. And this is again censoring assumption. So the next is the unconditional hazard ratio. So log hazard ratio, and this is defined by the Cox model that include only the treatment indicator. So the hazard ratio, in order for that to be defined, this needs to satisfy proportional hazards assumption. And or we care about like stratified hazard function per arm. If we want to test their equal across the treatment arms, we use stratified log rank test. Or another estimate we might care about is the stratified log hazard ratio, and this is defined by the stratified Cox model that include both the treatment and the stratification factor. So this data will have different interpretation than this data. But these are commonly used to estimate in survival trials, and covariate adjustment methods have been developed for this estimate, which target the same estimate and then still make the same censoring assumption. So the covariate adjustment methods for survival function, unconditional survival function, is proposed in Zhang 2015. And then for the rest of this, they are proposed by Lu and Tiates in 2008 and our paper in 2024. So the key idea of these covariate adjustment methods is that we will take the statistic from the unadjusted methods, and then we will linearize them to obtain what I will call derived outcome. And then we take this derived outcome to fit regression, do covariate adjustment. So that's the pipeline. So it adds a linearization step before doing regression and covariate adjustment. So this makes sure that we target the same estimate and assumption under the same assumption as the unadjusted analysis. So I'll show two examples just to give flavor of how we do covariate adjustment. This is for the covariate adjusted log rank test. So we know like the standard log rank test, it will look like this, where we have the numerator being the score function from partial likelihood, and then the denominator is essentially a variance estimator of the numerator. So that's the standard log rank test. And so what we do is to linearize the numerator, because the numerator has quite involved terms with all the risk set calculation involve all the participants in the data. So what we do is just to linearize it and make sure it looks like an IID summation. So once we linearize that, I'm not including the formula in O hat, but so you can see that now the numerator will just look like ANOVA. So it looks like having the OI1 hat and OI0 hat as the derived outcome, then just do contrast of two arms. Then once we linearize, we will take the O hat as a derived outcome to fit a linear model. So once we fit a linear model, we will take the coefficients and subtract terms that look like this. So the coefficients are from that linear model of OIJ hat on the X. And then these adjustment terms, it works because we can see that they are estimators of zeros because the covariates are balanced across arms. So the flavor of this is that we just obtain the original log rank test numerator and subtract something. And this thing is estimated by linear regression to make sure it always reduces the variance of the statistic. And this adjustment terms is always estimators of zero, meaning that it doesn't change the interpretation of the numerator. So that's the numerator. And then we correspondingly derive the denominator, which is the variance estimator of the numerator, which is guaranteed to be smaller than the original log rank test denominator. So we have a theory for this test statistic, which denoted by TCL, the covariate adjusted log rank test. We say that under the same null hypothesis and assumption needed for log rank test, if, again, all the joint levels of the stratification factor is used for covariate adjustment, then this test statistic this test is asymptotically valid, universally applicable, and guaranteed to be more powerful than the log rank test, regardless of the true data generating process and which randomization scheme is used. And the denominator takes this form, which is just the original log rank test denominator minus a variance reduction term. And with this form, you can see that TCL, it reduces to the standard log rank test if the beta is equal to 0 when there's no covariate adjustment. But if the beta is obtained from this linear model, it's guaranteed to reduce variance and it's guaranteed to have power gain. And a similar result for covariate adjusted stratified log rank test is also obtained. So that's for the test. Now we have more powerful test than the log rank test, still testing the same null under the same censoring assumption. Now, after test, we usually like to also report an effect estimate. And what we usually report is from fitting a Cox model that just include a treatment indicator. And this makes sure that the test, the estimate from the test and also the hazard ratio is sort of in correspondence. So for this estimate that's defined by this Cox model with only treatment indicator, we can also do covariate adjustment to improve efficiency of the estimation. So the idea is very similar. To estimate this estimate, usually we use this, the standard approach is to use this score equation derived from partial likelihood. And this score equation has this parameter theta that we want to solve for theta making this score equation equal to 0. And that gives the standard Cox model estimate. That's the unadjusted estimator. And now we can also linearize. Like once we have this score equation, we can also linearize them to make it look like this, which is quite similar. The difference is that the derived outcome now depend on this parameter we want to solve. And then we obtain covariate adjusted score function by applying any covariate by still adding these adjustment terms. So these adjustment terms, they are again estimates of 0. So it doesn't change the interpretation of the score equation, but it reduces variability of the score equation. And we solve this covariate adjusted score equation, give us the covariate adjusted estimator. We also have theory for this estimator, but intuitively, we know that if we do any COVA approach to construct these linear adjustment terms, the score function has reduced the variability than the original one. And then the derivative or the Jacobian doesn't change because the adjustment term does not depend on the parameter. And so by a standard argument of M estimator, we know that this estimator after covariate adjustment is guaranteed to have smaller variance than the original one. But it has the same interpretation as the original one and is valid under the same assumption, same censoring assumption compared to the original one. Okay. So now I just want to show how the survival estimator perform in this example of ACTG 175. It's an HIV trial, and the primary endpoint is a composite endpoint defined by this. And this trial does stratified permitted block randomization. The treatment arms, there are 4 treatment arms, but here I just take 2. So it's the didanosine compared to zidovudine. And then the covariate adjustments we use is the baseline CD4 cell count and number of days receiving prior antiretroviral therapy. And here are the unadjusted Kaplan-Meier, just standard Kaplan-Meier for all the participants and then for these 3 subgroups. And we see there is some clear separation of the Kaplan-Meier for overall. And across subgroups, it looks like the Z equals 1 and Z equals 3, they correspond to no prior therapy or like larger or equal to 52 weeks of prior therapy. They look their separation, but the middle group, which has 1 to 52 weeks of prior therapy, it looks like there's no separation. And then we apply the standard log rank test to the data, and then also the covariate adjusted log rank test. So we separately report the numerator, denominator of the statistic, and also the p-value. So here we can see, first we can see that the numerator is basically all quite similar for the log rank test and covariate adjusted log rank test because they have the same interpretation. This one just adjusts an estimator of 0. So this tends to be more precise. So more precise at the true value, but it doesn't change the interpretation. Then we see the denominator. And from the denominator, we can see that the covariate adjusted log rank test in general has smaller denominator, smaller variance estimator of the numerator. So that's what we expected, and this holds true for all participants or for the subgroups. And then, so the overall is quite significant, so both tests are significant. But if we consider subgroup analysis with Bonferroni correction, then there's actually gain from doing the covariate adjusted log rank test. This is has more significance than the unadjusted ones. Okay. So lastly, I want to just spend a couple of minutes on some practical insights. I talked enough of theory. So the practical insights are just the points I want to highlight for implementing the covariate adjustment in practice to maximize efficiency gain. So the first one that's often ignored is that in practice, if we have multi-arm trials, it's quite common to subset the arms for comparison. like I did in the survival data, the ACTG example. But actually, it's better to not subset the arms for comparison and use the full data. And the intuition is that the arms that are not in comparison, they're covariate, are still useful. So here is an example that if we are interested in arm 2 and arm 1 comparison, but this is a 3-arm trial, then from the ANY-COVA estimator, this is what we obtain from this linear adjustment, then we can see that if we consider the model using 3 arms, then using 3 arms give us a more precise estimator of the overall covariate mean. So that can lead to noticeable efficiency gain compared to just fitting an ANY-COVA estimator for the 2 arms. So the overall intuition is that just the covariate data for the other arms that are not in comparison can help us to improve efficiency, and it's free efficiency gain. So more generally, for the AIPW estimator, that's also for arm 2 and arm 1 comparison, it will look like this. And now we can see that this G-computation term, that this term, if we use the full data, it can also use all the data across treatment arms. And that uses all the covariate data across all the treatment arms. So it's quite robust and it's quite intuitive. So this can give us efficiency gain. So first thing. The second thing is that it's actually important to account for covariate-adaptive randomization or stratified randomization to like take advantage of that and not being conservative. Or you can use universally applicable approaches like I mentioned with ANY-COVA and others. So this is a simulation example. It's meant to a little bit exaggerate the point, but this is to show you that in this case, the standard log rank test under stratified primitive block can be conservative, and that can adversely affect the power. But if you correct the conservativeness that we proposed in a JRSSB paper earlier, it can lead to efficiency gain. But if you further adjust for covariates, so adjust for stratification factor as well as other covariates, then the covariate adjusted log rank test can give more efficiency gain. And the third point is that the covariate adjustment that is usually for a small number of covariates for 2 reasons. The first is to guarantee type 1 error, like to have better finite sample type 1 error control. And the second is to have more more guarantee on power gain, because if you adjust for a large number of covariates, there may not be power gain. You may have power loss because you estimate too many parameters. So in practice, if there are many covariates, then there are a couple of approaches that are available. So the first one is that you can potentially perform variable selection, either using with the cross-fitting, right? So we saw earlier with the AIPW, we can do cross-fitting. Then actually that can also incorporate variable selection methods. And so this is studying a recent preprint by Van Lanker. And also we have a last discussed point about many covariate is that actually the mental Hazel methods can, if under the sparse stratum setting, it's effectively adjusted for many stratification factor. So this is also a way to adjust for many covariates. So we have some paper that's led by my students, which study this estimator in both as a covariate adjustment approach for both the large stratum and sparse stratum. And what we note that is we can have a method that guarantees type 1 error control for both the sparse stratum and large stratum, but the power again is uncertain, right? So if we only have a few strata, then there's usually power gain, but if we have like too many strata, the type 1 error is okay, but the power gain is not certain. And finally, the covariate adjustment methods we can do it in both interim and final analysis. So doing it in the interim analysis is recommended because if we have more power from the covariate adjustment methods, then it's more likely to like declare effective to declare efficacy in the interim analysis. So there's potential to stop the trial earlier. But one needs to adjust for the fact that covariate adjustment is used in both interim and final because the standard independent increment argument for the group sequential design is not very rigorous in this setting with covariate adjustment. So there are methods to fix that. So the first one is to proposed by Van Lanker is to orthogonalize the estimator to still get independent increments. And the second approach is to recalculate the critical value, usually at the final analysis, by accounting for the variance, like the covariance of the tested statistic in the interim and the final. So this is by joint normality, and you can estimate the variance by bootstrap, etc. So if you don't want to calculate analytically. So this is one summary of what I talked so far. The covariate adjustment can be applied to any outcome type to improve efficiency while maintaining the same estimate and assumptions. And unadjusted, linear adjusted, and G-computation estimators, they are all special case of AIPW estimators. So we have one asymptotic theory of AIPW that covers all estimators. And the ANICOVA is the core to achieve guaranteed efficiency gain and universal applicability simultaneously. As you have seen, we apply this to in both the linear adjustment GLM with the joint calibration or the survival data setting with where we apply ANICOVA to the derived outcomes. And here are the main references from my group. So all the methods are available in RobinCAR package. And RobinCAR 2 is a package that's in development. It's a light version. Right now, it only has linear and nonlinear adjustment. So if you only want to do this two, then the RobinCAR 2 is preferred because it has less dependency. And so for this two, it will be the same as the RobinCAR, but it has less dependency and a different user face that may be more user-friendly. Currently, the survival analysis methods are still in development and being developed for the RobinCAR 2. So stay tuned. Finally, just the advertisement of our working group that has a lot of interesting activities about like blogs and seminars and software. So if you're interested, you can follow our website or follow our social media at LinkedIn. Thank you so much.
Yeah, thank you so much, Professor Ye, for a great presentation and some overview of the existing methods and also some exciting new development. Yeah, I think we probably have about 10 minutes for discussion. So I think if you have any question, please feel free to unmute yourself, or if you want to use the chat, that's also fine. While we're waiting for questions, I do have one question for Professor Ye on the practical side. I think you talked about there seems to be different ways of utilizing stratification or covariates, right? For some factors or variables, we may have the option to use stratified randomization or using use it in the analysis or even both, right? And there could also be the case that maybe for some variable, it's possible to do stratification because they are categorical variable, but for some, they are difficult to do stratification because they're continuous in nature, for instance.
Mhm.
So I'm wondering from the, um, from your perspective, what's the best strategy to prioritize among these steps?
Yeah, thanks, Don. That's a very good question. Um, So for stratification, usually I see like two types of variables. One is variables that are thought to be most prognostic to the outcome. If it's discontinuous, then of course we need to discretize it. And the second is more like for administrative reason, if it's like different sites or countries, then people also use that in stratification. So the stratification, like stratified permutive block, works the best with like a small number of stratification factor. Otherwise, if it's too sparse, then it doesn't achieve much better balance. So usually just like most important prognostics and maybe some for administrative reasons. And I I would definitely recommend still do stratification for the most important prognostics because it gives us a more balanced data to start with. Although if it's unbalanced, we can still adjust for that in the analysis stage. But finite sample, it's better to do both. And also it's likely to show with the stratification, it gives us more balanced data to start with. That can avoid some potential like very extreme problems, such as in one strata, it's very unbalanced, so it's very hard to fit model, etc. So um, yeah, that's what I want to say. And it's effectively, I mean, um, adjusted for the stratified by the most important factors and in the design stage. And then in the analysis stage, we need to account for that. Otherwise, we will have conservativeness. And also we can adjust for more variables that are thought to be prognostic to the outcome.
Got it. Thank you. Just to make sure I understand, so I think it would be great to pick maybe a few most prognostic variables suitable for stratification to prepare the data in a balanced way within stratification, and also include them in the analysis model, maybe together with some other prognostic variables.
Exactly.
Got it. Got it. Thank you very much. That's clear. We do have some question. I think there's one question about, I don't know whether that's a question or comment. Maybe the question is about installing Robin Car package in R or R Studio. Um,
Yeah. Um, the Robin Car package is available on CRAN, so you can download it by like install.packages. Uh, the the CRAN version is quite up to date, so I don't see a reason to download GitHub version.
yeah. So Hong, if you have follow-up questions, please add. And there's another question about whether the slides and recording will be shared. Yes. After the meeting, we will share those. Thank you. Yes, let me see. Do we have other question or comment?
Hey, Ting Ye, thank you. Hi, Dr. Ting Ye. Thank you for great presentation. And I'm Ke Zhu from NC State, and I have a question about TMLE. We know that TMLE may have better finite sample properties or performance compared to the AIPW. So does it also hold for covariate adjustment in RCT, or does TMLE have similar nice property such as guaranteed efficiency gain and universal applicability? Thank you.
Yeah, that's a very good question. So the TMLE, I mean, in the simple case with like uh, linear adjustment or GLM adjustment, they are the same as the methods I talked about. So in more complex scenario, then it's yeah, I didn't like do simulations of TMLE to see how if they are like they have better finite sample performance than the AIPW estimator. But that's definitely interesting for like future investigation.
Thank you very much.
Thank you very much for that question. Yes, so while we're here, I just want to quickly follow up on that. So, Professor Ye, could you share maybe some future directions in case we have some researchers in the audience who are interested in this area and want to do more research in this area? Would you like to share some ideas about some open question, interesting directions for future research?
Yeah, that's a good question. So one thing will be like for different estimate, especially in survival data analysis. There are like a lot of other estimate of interest. It will be of interest to study how to do covariate adjustment for this other estimate. The second is more about like these future like this. So these topics including how best to do variable selections with covariate adjustment in clinical trial if we have like a large number of covariates. And the next one I want to say is like another topic is how to do covariate adjustment in more complex designs. So right now with quite standard parallel group design, then it's clear. But in practice, we also use other more like adaptive designs or so other designs in clinical trials, how to incorporate covariate adjustment in those other design. And finally, I want to say more practical investigation will be of interest. So right now, the covariate adjustment methods for the contents I talked about are well established in theory, but more like simulations or more like real data based analysis will be important to understand their performance in practice. So for example, I've seen like I worked with some groups in company, and then we have seen quite interesting phenomena, such as the methods perform differently with balanced or imbalanced design, and like there is also different performance with like if you do stratified log rank test versus if you don't do stratified log rank test, but instead adjust for the stratification factor in the standard log rank test. So how to consider these factors? So I definitely think like more numerical investigations will be really interesting to understand all these things.
Yeah, thank you very much for sharing those. Yeah, I think we are on time. And thank you all for joining today. Especially thank Professor Ye for great presentation and share your ideas with us. And I hope everyone enjoys the weekend and look forward to you in future ISBS webinars. Thank you very much.
Thank you so much. Bye.
Bye.